In this video, I'll talk about the hydrohalogenation of alkenes in the presence of hydrogen peroxide, which I can write that as an H2O2, and sometimes you may also say as an ROOR. So R could be any alkyl groups, could be methyls, could be ethyls, or anything like that. Now, when you run hydrohalogenations in the presence of peroxides, it does an anti-Markovnikov addition, as opposed to if you run a regular one. For example, if I'm running an addition reaction to this alkene here, let's say the propene here, just in an HBr, no ROR on the first example here. So the solvent could have been just CCl4 or dichloromethane. That would actually go through the formation of carbocation. So the first step here would have been the addition of the electrophile, which is going to be the hydrogen. So you use the double bond to grab this proton here, and this bond goes on to the bromine. So as a result, it makes a carbocation, so your hydrogen will go to the terminal carbon so that this carbon can get a positive charge. Because when you going through in a carbocation radicals or anything like that, you want to make sure you're making a more stable carbocation here. And then you would have the Br minus kind of on the side here. So the next step here would have been the tack of nucleophile onto that electrophilic carbon, and in this case the electrophilic carbon would be your carbocation carbon. So then I can have a top and bottom attack, so as a result this could make a pair of enantiomers, but since this is not going to be in a chiral center at the end of the day, or I can also say this is not in a prochiral center, I don't have to worry too much about the stereochemistry. So I go ahead and add in a bromine here. So the addition of bromine in this particular case was ran with according to Markovnikov's rule. But if I'm using ROR, it does not do Markovnikovs, but rather it does anti-Markovnikovs. So just literally the opposite of Markovnikovs. So what I'm going to have at the end of the day is the bromine, instead of going to the middle carbon or more substituted carbon, is going to be going to the terminal carbon, or the carbon that has more hydrogens to begin with. That's how you want to think of it. So if I go back and look at, there is a hydrogen here and a hydrogen here. So there's two hydrogens here, and then there's only one hydrogen to the middle carbon. So when you run into Markovnikovs, you can say your electrophile or the hydrogen will go to the carbon that already has more hydrogens. As a result, you can make a more stable carbocation. But when you run an anti-Markovnikovs, it would have been the otherwise. Your hydrogen will go to the middle carbon, or the carbon that has less hydrogen atoms, and your bromine or the nucleophile at the end will go to the carbon that has more hydrogens to begin with, which in this case is going to be this guy. So that's the product that you make here. So this is going to be anti-Markovnikovs. The difference really lies in how the process takes place. The first reaction actually goes through the formation of carbocation, but when you run the HBr in the presence of peroxide, this does with the help of, or this goes through the radical mechanism, so it makes a radical in the process. So let's talk about that mechanism for a minute. Now, if I'm running in a radical mechanism, I got to make sure I am able to create the radical to begin with. So the ROR, or the H2O2 that you're using, is going to be the one that's going to be creating the radical in the beginning. So how do I create the radical here? Well, I can go ahead and use ROR, or H2O2. So let's say if I'm going ahead and using H2O2 for my example here, so I can go ahead and write this as something like this. Or if I'm using ROR, I can show it like this. So I'm going to have a homolytic breaking of the bond here, where when this bond breaks in the middle, it's going to have one electron going to one oxygen and another electron going to the other oxygen, something like that. So then at the end of the day, I create this radical here. So remember, your oxygen already has two lone pair of electrons to begin with. So I can go ahead and draw those here just to kind of see them better. But then when you break the bond, you will have one electron going on to one oxygen and the other electron going on to the other oxygen. As a result, you'll have one electron that's going to be unpaired by itself. So I can write it like this, or sometimes you may see things being written as HO with one electron in here, and that's assuming that you already got the two lone pairs on that oxygen. Sometimes you don't necessarily have to write them. So when you have an atom, like, or this particular molecule, and you can say with one electron by itself, that's what's called a radical. So you create the radical here, and I could have done the same thing. I could have made OR here, two molecules of OR, and that is going to be in a radical in there. So now I have created the radical. My next step would have been to just go ahead and start with the molecule here and then see how that's going to look like. So I'm going to go ahead. That was an initiation step. The initiation step is indicated by starting with a molecule and creating a radical. So that's how you know it's an initiation step. So then now you can have a propagation step where I can say that I'm going to go ahead and break, I'm going to go ahead and use this HO here as an example, or HO radical here, and I'm going to use HBr here. So since we are already doing this with the radical mechanism, I can go ahead and break this HBr within a radical as well. So when I go ahead and break this within a radical, I'm going to go ahead and have one electron going on to the hydrogen, one electron going on to the bromine, and that one electron gone on to the hydrogen, and this um, OH radical here is going to get combined to make water. So I do make water here, and then I would have the bromine radical. So remember, the bromine actually already has three lone pair of electrons. So I'm going to go ahead and draw those out. But now you have one electron by itself, and that's what makes this a radical here. So this is in a propagation step. And how do I know it's in a propagation step? A typical propagation step is going to be where you're starting with a radical and a complete molecule, but then you're creating another molecule and another radical. So if I was using ROOR, or the OR radical here instead of the HO, then I would be making an alcohol instead of water. So the method would still be the same. Here I would have RO radical, and here I would make an alcohol at the end of the day. So this is one of the propagation steps. You can have multiple propagations. So now if I'm starting out with an alkene here, I'm going to go ahead and break this apart homolytically again. So I'm going to go ahead and break the pi bond, have one electron coming down here and another electron coming down onto this carbon. And I'm going to be using this bromine radical as well to kind of make a bond with this terminal carbon. Now, the reason why I want to make a bond with the terminal carbon is when I do so, I actually create a radical. So this is the new bond that's between the carbon and the bromine. I create a new radical that's going to be right in the middle here. That's going to be your secondary radical. Now, if someone say, why not using this carbon's radical here and combining with the bromine? Well, if you do so, your bromine will go to the middle carbon, but then this carbon eventually would get the radical, and that would be in a primary radical. So remember, I gotta make sure I'm going through in a more stable radical. So this is again a propagation step. So on at this point, I can go ahead and do a few things. I can go ahead and use this right here in the next step, and I can say I'm going to go ahead and use HBr because you already have the radical created. So I'm going to go ahead and break this apart homolytically, and I'm going to go ahead and use this radical to combine with the hydrogen radical here. And as a result, you get the hydrogen in the middle carbon now, and now you already got the bromine on the terminal, and you create another bromine radical. So this kind of cycles goes on and on. So this would be another propagation step because you can kind of see how it's still kind of going on. You haven't really killed the radical, and you're not really creating a radical either. So like even in this previous example where we started off with a radical in a molecule, created another set of radical in there. The last step would be in the reaction that you have to kill off the radical, and that would be the termination step. And termination step could be anything. So I could technically have a bromine radical, or a matter of fact, two bromine radicals kind of coming together and making it a bromine molecule. Or I can have a hydrogen radical and a bromine radical. So at the end of the day, what is really available in the reaction mixture and that can do the job? Or I can even have something like this radical, and I may have a hydrogen radical floating in the mixture, and that would combine together to make a molecule. As long as I can kill the radicals, that's what's going to be the termination step. And you can have different ways of drawing termination, different types of termination steps, and as a result, sometimes you get multiple molecules. But there is always going to be one product that's going to kind of dominate over the other ones.